Hi. Usually, I like to sort of focus more on more in detail about students' research. So I will not give a high-level talk. I'll give a more kind of in-depth talk about what some of my students have been working on. And I will focus on three. I worked a lot on cognitive radio and spectrum sensing techniques and studying spectrum in general. Some of my students that worked on this are listed on top: Harris, Goran, and James. And some of the co-advisors involved are Ivan, Larry, and Veliki. I'm sure I missed some of them. What are the topics I'll focus on? I'll focus on our early work where we try to study the propagation environment of orbit. The second talk is, I guess, the longest talk about Goran's work on what I call radio scene analysis. And I will just introduce or advertise James's talk, which is going to be lost in the schedule, on surfing for channel occupancy estimation. Some other topics that we also covered at WINLAB were vehicular channel spectrum sensing, and the other one was white space sensing. Jonathan and Dushan worked on this, and what I don't have right now on the slides, which is, I guess, a miss, that some of these projects were related to and were inspired by works of companies like Toyota, ITC, and NEC Japan. Okay. So let me just sort of briefly talk about. I just also want to mention that the talks that I'm going to talk about today, first two are co-advised with Ivan, who's going to talk about WISER after me. Okay. And everybody knows Ivan. So Ivan actually sort of led this project, and this project was also important for our Goran's work, where Harris really did hands-on work to characterize the orbit radio testbed. Basically, this is the picture, right? You have orbit in the corner, and Ivan got some 60 feet low loss cables and used the vector network analyzer to have two transmitter and receiver very far in the orbit room. I guess this is the picture if you see orbit. And transmitters in the corner, and the receiver was moved. It was really quite a contrapture, and we tried to sort of find out what happens in orbit. Why do we want to study orbit? Because many people would like to experiment in orbit rooms, so we'd like to see the propagation environment. I'd like to know what happens there. Okay. Also, these are realistic channel studies, which we can use later for simulations. The environment is indoor, and we care about basically ISMU and IA bands, the ones that we're going to use in the testbed. Most of them are 100 megahertz bands, so we needed wideband study. So just to give you an example of results, you can see that at some points along this line that you saw here, right, at distance 11 meters, you see that the channel has dips somewhere between 10 and 15 dB. Okay, so Harris actually was really, did really some good work in the sense that he tried to see what he gets with the WISE simulator, which is a ray tracing simulator that he got from Crawford Hill, Bell Labs. And he said, okay, let me compare to what the measurements I get and the measurements that WISE will predict. Okay, and you can see these red lines on the, we don't have any pointers here. The red lines that correspond to WISE predictions in terms of reflections, and you see the blue line which kind of follows that, but some of the red lines are not really involved in the blue lines. And Harris explained that by the fact, and we later studied the radiation pattern of the antenna, and the radiation pattern of the antenna really didn't allow the reflection from the ceiling and the floor to really show, and WISE did not predict that. Okay, but the rest is quite remarkable in terms of the delays and so on. So for us in studying what comes later is like we took these channel response magnitude results and we used them in some of the simulations to get actually quite realistic results in terms of simulating the signal, simulating the channel, and studying the spectrum occupancies. Okay, so the again, Goran tries to not use that term, but I like to call this radio scene analysis, is again co-advised by Ivan and me. And what we do, we focus on packet-based radio. So what you should think of UNII and ISM bands where you have Wi-Fi, Bluetooth, and cordless tone type of, thank you, cordless tone type of transmissions. So transmissions are off and on, and they are using, like Wi-Fi does, uses this 100 megahertz band at will, right? And we'd like to study in this band what really happens, okay? And part of the different thing to what they call spectrum sensing in TV, for TV, which is 802.22, is that these transmissions are on and off. So to study them, you really should understand what's the activity factor and what's the occupancy. Is it, maybe some channels are visited once in a blue moon. So for our purposes, they're also open, even though some techniques will call them taken. So this study is basically focusing on availability of channels in UNII type of ISM bands, but the techniques are very open in the sense they're non-parametric, so these techniques can be used elsewhere too. So the idea is that you have transmitters which are red and you have sensors which are blue, and the sensors which are blue, they're trying to study the transmissions from the transmitters. Very simple, and this is some of the things which we'd like to do is try to find the spectral occupancy, try to find the activity sequences in time, and potentially find where these transmitters are. Okay, and that depends on how many sensors do we have. Maybe we can do a lot with just one sensor, which actually we show that we can. So basically, what I determine as goals is to find the spectra of the transmitters, on-off activity sequences, and channels. And for that, we use a two-stage algorithm, which is, first one is based on signal segmentation, and the second one was based on a fourth-order spectrum-based analysis. We have some experts here on this topic. Athena wrote a book. The mean shift analysis, which we use here, has been used a lot in computer vision, and Professor Mir from our department has been one of the spearheads in this technique, and we found it quite useful. So what's the goal? The goal is to basically segment in time intervals that behave the same. Okay, so some intervals don't have any transmissions, some intervals have one transmission, some intervals have two simultaneous transmissions. Okay, and we want to put them in bins. Okay, we want to cluster them. Okay, so the simplest example is if you have one sensor and one transmitter, and you can always think of this box as being the orbit room, right? And okay, so we're going backwards in time. We're using 11B, right? So once the source is transmitting dBPSK with Barker sequence. Okay, and we use, like this is orbit room, and we actually physically use for that node the channel to transmitter measured by Hars. Okay. So what do we do, right? We look at the spectrogram, this blue thing. I'm not sure how clearly you see it right now, but these basically the bandwidth of these big blocks is 20 megahertz, and the duration is about 1 millisecond of each packet, and they're on-off. Okay. So if you and this is one packet, another. So in between, there's nothing. Okay. So basically, if you look at this time, you can beam these into a part where there is a transmission, there's part there's no transmission. So those are two clusters. Okay, if I put these clusters in these measurements of powers, just powers, right, I get one cluster for the time when there's no transmission and another cluster when there's transmission. Of course, these two clusters come close together if the signal-to-noise ratio is small, but we'd like to find the centers of the clusters and we'd like to sort of bind them to get the activity. Okay, so we have to go a few stages, and the first iteration with MSA will give us some spurious results, and there are techniques which we use to segment them, okay? And then here you can see that this is when there's no transmission, this is when there is transmission, and so on. Okay, very simple. Well, simple conceptually, but how do you execute it, how do you make it work, and so on, right? There are a lot of technical details, including what is the resolution that you measure, let's say, power spectral density, and how many bins of the power spectral density you should use, and so on. Okay. So if you would like to, and there's a trade-off, right? The smaller resolution that you use for PSD estimate, these edges are easier to find, but the longer these intervals of measurement intervals are, the more reliable measurements you get. Right? So how about, can we do something smarter? Can we fuse measurements for different segmentation intervals fusions, right? Measurement interval fusions, which we call multi-resolution segmentation. You can see this is multi-resolution in time. Okay. You can also envision multi-resolution in frequency. Okay. So we do all of this, but I'm just giving you an example of multi-resolution fusion in time. And what you see here is detection rate of finding the number of clusters. The SNR goes down, even that is hard to do. Okay? See, we don't assume that we know the number of clusters. Okay, what is the error rate in terms of like, is our binning into clusters correct? If the SNR goes up, it also blows up. Okay, and here you can clearly see that the detection rate will depend. Like this red line corresponds to 20 microseconds. This green line corresponds to measurement of 10 microseconds, and this blue one corresponds to 5 microseconds, right? Okay, so if we don't know the SNR in advance, right, what do? Well, we can basically use all three and fuse them and get a measurement that kind of basically follows the best of all three. Okay. What if we have multiple sensors and we'd like to do something better? We'd like to work with lower SNR, or we'd like to work with an environment where these measurements are done at different SNRs. Okay, so of course we use the same diagonal that Harris designed, right, with one transmitter and 4 measurement points. Okay, and then we fuse these as you can expect. We basically, so you see sensor F3 is really not doing well, right? Sensor 4 is doing better, but the sensor 1 is best. But we don't know which one is best in advance because it depends on the location of the transmitter. But we can, when we combine the results of these segmentations, we can fuse the results and get the one that is doing the best. Okay. So once we segment, right, what do we do next? Okay. Once we segment, we really don't know too much, right? We know that maybe some segments correspond to 3 transmissions at the same time. A Bluetooth that overlaps and collides with a Wi-Fi. Okay, but we have to resolve the 2 transmissions. If we'd like to understand better the spectrum, we'd like to know who's transmitting, what's transmitting, what is his power spectral density, what is the transmitter activity in time, and maybe what is the channel to the sensor and so on. Okay, so that for that we have to go further, right? But once we have the segmentation and we understand that things are kind of stochastic and static in time here and there, all these that are similar in time, we can group together and study them together. Or we can study all of them together, knowing that some transmitters are active here and there, and these segmentation intervals may be different, but still the activity is engaged in all. Okay, you can sort of like envision this, perhaps. Okay, but one sort of like immediate thing that you say, once I found these activity intervals, like if I look at the Gaussian noise and I do my PSD, there's no cyclostationarity, and I get my noise value here. If I look at these, I have a dBPSK, which is cyclostationary, and the spectra at this k over t is related. So I can study them separately. All of these techniques are usually based on assumption of stationarity, but now that I sort of found stationary intervals, I can do this easily. Okay. So what's the goal of our transistors? In our case, we're going to use fourth order spectrum, and we're going to find activity patterns for different possibly overlapping transmitters. For this, we need blind source separation techniques. We would like to characterize the channel to sensor spectra, and if possible, we'd like to decompose the channel spectra and the pulse spectra too, which is a part of what we call blind deconvolution. So for this purpose, we use a specific slice of a fourth order spectra, or so-called tri-spectrum slice. Okay, that slice has very nice properties in the following sense. That if you take, like this is P goes over transmitters, and if you look at a single segment where so many transmitters are active, C is an index of how many which transmitters are active, right? So if C is equal to 0, transmitter 1, C1 is equal to 1, then transmitter 1 is active. Okay, we have M transmitters. This is the channel from the sensor to the transmitter, and this is the PSD of the transmitter itself. This is the Gaussian noise spectrum. Turns out for this slice, for our fourth order spectra, of course, as you know, this is 0. So we don't have to worry about noise. That's a good thing. Okay. And now we'd like to kind of decompose, right? Because some of these overlap, we'd like to decompose them over time to sort of find out which one is which and which one is whose. Okay, for where R runs over different segments that we made earlier. Okay. So for this, we use something that Athena has used many years ago and maybe still uses. It's called Tensor Decomposition, which is unique under many conditions. So I'll probably hurry up because I took all of the time. And I'll give one example, which is, I think, the key. Bluetooth versus 802.11b interference, and this is one Bluetooth and this is one Wi-Fi, or the reverse transmitters. Okay. So the picture is very similar. Frequency, time, this is Wi-Fi, 3 Wi-Fi packets and 2 hops of a Bluetooth transmitter, and they are colliding. As you can see, these Bluetooths are very high power, but 1 megahertz bandwidth, and these are 20 megahertz bandwidth and time. Okay, so this is a complex situation. Can we study this, and can we deconvolve it, and can we find activities, actually separate the activities of the Wi-Fi and the Bluetooth? Okay, right now what we can do in the first segmentation is find those intervals that look the same, right? These look the same that are white, and these look the same that have no Bluetooth, and this one is very unique, and this is another one that is very unique. Okay. So we study techniques which basically find the number of ranks in the signal and find the number of signals, okay, basically, and study them as a function of SNR and so on. Okay, so this is, I guess, what's the result, right? What you expect is that we do find a spectrum of a Bluetooth signal in that one hop, spectrum of the Bluetooth on the other hop. This is when the hop happens, this is when the second hop happens, and this is the the Wi-Fi signal, its spectrum with dips due to orbit channel, and these are the transmissions, okay? And the noise active all the time. Okay. So that's all I want to talk about this today.